Thanks for the nice introduction, Anna. Okay, so I can see lots of audience here. I can see my advisor and our group members. It's nice. Hope you find this seminar interesting. All right, good afternoon, everyone. It is great to be here with you today. I'm going to talk about recent work done by our group. It's about the silicon-25 beta-decay spectroscopy using the gaseous detector with the germanium tagging system. This presentation is divided into 4 parts. The first fundamental question is why we study beta-decays. There are 2 main motivations. The first is beta-decay spectroscopy provide detailed nuclear properties and the structural information, which lead to stringent test of fundamental symmetries and interactions. And the second is it also deepens our understanding of the nuclear processes in explosive stellar environments. To get started, let's take a look at the chart of nuclides. And we all know most radioactive isotopes on this chart decay by a process called beta decay. For nuclei near the neutron drip line with large Q values for beta minus decay and low neutron separation energies often decay by beta delayed neutron emission. And similarly for nuclei near the proton drip line with large Q values for beta plus decay and low proton separation energies often decay by beta delayed proton emission. And so let's zoom in on the nuclear chart. During my PhD years in China, I have been focusing on studying the beta decays of nuclei close to the proton drip line in SD shell, which is highlighted by the blue circle here. And meanwhile, on the other side of the planet, another research group led by Professor Chris Wrede at NSCL has been focusing on measuring the beta decays of proton-rich nuclides in the same region, but with a different method. Just one day, I reached out to Chris. I said, hello, I'm a big fan of your work. Can I join you? He agreed to recruit me. So here we are. And I hope he hasn't regretted that decision. Okay, back to our topic. Silicon-25 is also located in this region. It's also the first beta-delayed proton emitter ever discovered. So far, the beta decay of silicon-25 has been one of the most studied cases. It has been measured by scientists in North America and Europe and also Asia. Because its beta-delayed proton branches have been so extensively studied, silicon-25 was chosen for commissioning of our newly developed GADGET detection system. Our experiment turned out to be more sensitive than our previous measurements, and the new structural information has been obtained. That's what I'm going to talk about in this presentation. Our experiment was conducted at the NSCL, short for National Superconducting Cyclotron Laboratory. Argon-36 primary beam was accelerated by the coupled cyclotron facility. Then the secondary silicon-25 beam was produced via the projectile fragmentation of the argon-36 beam impinging on a beryllium target, and then purified using the A1900 and the radio frequency fragment separator. The photo of this experimental setup is shown at the bottom. Our detection system is called GADGET, short for Gaseous Detector with Germanium Tagging, which is comprised of the gaseous proton detector in the middle and the segmented germanium array the germanium detector, or we call it the SEGA detector. In the silicon-25 experiment, we collected data for about 9.5 hours, a total of 3 × 10⁷ silicon-25 ions were implanted into the proton detector filled with the P10 gas mixture under pulsed beam mode. The longitudinal distribution is shown in the bottom right corner, and the beam transverse distribution is shown on the right side. You can see our the inode plane of this proton detector is segmented into 13 readout pads. Our group built this detector to measure weak, low energy proton decay. Of course, we didn't only measure silicon-25. That will be a waste of taxpayer money. To give you a big picture, we have measured our plan to measure the beta decays of several other other nuclides. For example, aluminum 23 was measured to study the sodium 22 P gamma reaction rate in the same campaign after the commissioning. And then the chlorine 31 decay was measured to study the phosphorus 30 P gamma reaction rate. Both of these two reactions are critical for understanding the nova nucleosynthesis. With these experiments, we hope to constrain the nuclear structure details that are most influential on the explosive burning of hydrogen on the surface of white dwarfs or neutron stars. The one shown in the last row is the magnesium 20 experiment. We are planning for the using FRIB to investigate the important oxygen 15 alpha gamma reaction of X-ray burst interest. And we also have a colleague analyzing the beryllium 11 decay. This one is more of an open question. It's associated with the novel decay and the neutron life anomaly. So here in the right column, we can see the intensity. It's getting more and more challenging. So it means we are pushing the sensitivity of our detector to extremes. And of course, except for the decay intensity, there are other issues that complicated the measurement and also the analysis. Anyway, the easiest one was silicon-25. It was assigned to me, and other more challenging cases rely on my colleagues shown here. Best of luck to you guys. So, okay, moving back to silicon-25. This is the beta delayed proton spectrum of silicon-25 measured by our proton detector. All 13 known proton peaks below 2.4 MeV are confirmed in our work, and a new proton peak at 724 keV is clearly identified here. So you can see the beta particle background in our proton spectrum is suppressed to as low as just 100 keV. So in my previous PhD experiments, we always use silicon implantation detectors. So the major problem for this method is the strong beta summing effect caused by energy deposited by beta particles. It's like for years we have been dedicating ourselves to developing solutions to suppress the annoying beta background. I would say the development of complementary experimental tools for the clean detection of low energy beta delayed proton branches is always valuable. So then we can also extract the silicon-25 half-life by fitting the count rate of all the protons in that spectrum as a function of time elapsed since the beginning of each implant decay cycle. Compared with all the previous literature values, our result is more precise and hence dominating the weighted average of all published half-life values. Next, this is the gamma-ray spectrum measured by the SEGA germanium detectors. 8 new beta-delayed gamma-ray lines and 3 new gamma-ray lines following the proton emissions are observed. So this is the higher energy region of our gamma-ray spectrum. We observe the gamma-ray lines as high as almost 7.9 MeV. So let's zoom in on a few peaks. Usually to extract information from the gamma-ray lines, exponentially modified Gaussian function or EMG function is used to fit each peak. This EMG function works well for the gamma-ray lines originating from aluminum 25. You can see the chi-square values are reasonable, but it cannot be used on its own to fit the magnesium 24 gamma-ray lines, which are emitted after the proton emissions. Why? Because the Doppler effect. So how can we accurately fit and extract information from this peak? We developed a Monte Carlo simulation to correctly model the Doppler effect. As we can see from the peak in the lower panel, compared with a regular EMG fit of this peak, this approach substantially improved the chi-square value and also the p-values of the fit. So to give you an idea how we did this, let's say after beta plus decay, a proton is emitted from a nucleus, then the daughter nucleus will recoil with the equal and opposite momentum as the ejected proton due to the conservation of momentum. If gamma ray is emitted while the nucleus is still recoiling, it will be Doppler shifted in the laboratory frame. So for an ensemble of such events, the resulting gamma ray line shape in the magnetic spectrum will be Doppler broadened. Then to accurately extract the information from this Doppler broadened peak, we applied a Doppler broadening line shape analysis, which took into account the energy of the protons, intensity of the protons, energy of the gamma rays, lifetime of the gamma ray emitting state, and the stopping power of our implantation material, in this case P10 gas, and also the response function of each SEGA germanium detector. In this case, the literature values for the first 4 inputs are already well measured, and the stopping power can be quantified using the code stream. Another input is the response function by fitting the previously mentioned unbroadened beta gamma ray peaks with the EMG function. We can characterize the parameters in the EMG function. Then finally, the simulation and data comparison can be done using the classical chi-square minimization method or the maximum likelihood method, which is better suited for low statistics analysis. So let's reverse our thinking. If 1 out of 6 inputs of the simulation is unknown, and the other 5 is the other 5 are known, then we can use the simulation data comparison procedure to constrain the unknown quantity, the unknown input, which is the lifetime, for example. And we have tested both solid and gaseous as the stopping material, and found that the solid material works well to excise nuclear state lifetimes in the femtoseconds to picoseconds range, and the gaseous material is suited for nuclear state lifetimes in the picoseconds to the nanoseconds range. It means this lifetime sensitivity range of this method basically covers most of the nuclear excited states. That's valuable. So initially, this technique, this Doppler broadening technique, was applied to the lithium-11 beta-delayed neutron emission, and the broadening is apparent for the beryllium-10 gamma-ray lines. As example is shown in the top right corner here. We extended this method to higher masses and applied it to the proton-rich nuclei, phosphorus 26 and manganese 20. The same gamma-ray line is shown in the two figures at the bottom. You can see the relative proton branches from two previous proton spectroscopies were used to separately fit the data. And it is easy to see that one of the two results failed to reproduce the gamma-ray peak shape. So even though protons are relatively easy to detect directly with good efficiency and resolution, some inconsistencies between the conventional spectroscopy experiments were resolved with this Doppler broadening line shape analysis method. So, let's since this new approach has wide applicability to both proton-rich and neutron-rich nuclei. So let's further imagine this the scientific value of this technique when applied to beta-delayed neutron emission. For example, let's extend this method to the island of inversion and to the mass region of ion and beyond, which is beneficial for our understanding of exotic nuclear structure, as well as of our process nucleosynthesis. So you may wonder why we need this method. We already have a powerful neutron detector arrays such as the Bpy and the Wrede, which were just discussed in the last EMP preview seminar by Yama-san. So, well, first of all, direct neutron measurements will not be superseded by our method. But we all know that detecting neutrons is more challenging than detecting charged particles or gamma rays. And the identification of neutron branches is often complicated due to poor energy resolution and limited statistics. Therefore, I think the development of complementary experimental approaches to study neutron-rich nuclei, like this Doppler broadening method, is particularly valuable. So now, at this point, we have measured protons, we have measured gamma rays, then we can conduct a proton-gamma-ray coincidence analysis. Here I show the two-dimensional proton-gamma-ray coincidence spectrum. You can see there are some coincidence shown in the blobs on this figure. Then with this, we can place all the proton and gamma ray transitions we measured in the silicon-25 decay scheme. For the sake of brevity, let's omit some proton branches. Then you may also wonder this if our work really yields any improved information for the decay of silicon-25. Looking back, let's take a look at the known silicon-25 decay scheme before our measurement, and adding our newly observed transitions to the existing decay scheme. You can see there we observed the new beta-delayed proton branches here, and new beta-delayed gamma-ray branches, and also new proton-gamma-ray coincidences. And moreover, the Doppler effect of the emitted protons on gamma rays was used to provide complementary measurements of the proton energies and intensities. All right, so this is a general overview. Now let's focus on some particular problems. First, we have measured the intensities of the beta delayed gamma rays, de-exciting the 2673 keV state, and the intensity of the 402 keV proton emitting from this state. Hence, this state is also called the 402 keV resonance in the context of astrophysics. For narrow resonance, the branching ratios here are highlighted in red, and the omega gamma highlighted in blue. The resonance strength are related by this well-known expression. So a previous mechanism 24 P gamma reaction measurement at a tunnel in North Carolina already determined the resonance strength of this state to be 41.6 MeV. Then combining the proton branching ratio and the gamma ray branching ratio measured in this work with the literature omega gamma value yields lifetime for this 2673 keV state of 2.9 femtosecond, which is consistent as well as more precise than the previously lifetime measured by the tunnel group using the conventional Doppler shift attenuation method. Okay, this is also a valuable piece of information. Then moving on, the silicon-25 beta-decay transitions can be compared with its mirror nucleus sodium-25, and also the theoretical model calculations. Here we show the decay scheme of sodium-25 and silicon-25. It's limited by the Q beta minus value. Only 5 magnesium-25 states were observed to be populated by sodium-25 beta-decay, and each one of them can be matched with a specific aluminum-25 state measured in our work. We can see that all the mirror energy differences are very small. So we believe the mirror energy symmetry is good. Then how about the mirror transition strength symmetry? Let's to give you a big picture, let's take a look at the mirror asymmetries reported in the nearby SD shell nuclei. This is phosphorus 26. This is a very comprehensive work done by our group. We highlighted in the green box here. We can clearly see the asymmetry between some mirror transitions between the phosphorus 26 and the sodium 26. Then also for sulfur 27 and the sodium 27, some asymmetries were observed. Then aluminum 22 and fluorine 22, the data are incomplete, but we still can see some asymmetries. Then we also have the magnesium 20 and the silicon 22 compared with their mirror nuclei. Here highlighted, there are also some degrees of mirror asymmetry observed for the nearby nuclides. So it's also worth mentioning that I showed the log FT values on the y-axis. So this difference will be enhanced when extracting the mirror asymmetry parameter, which is usually derived from the FT values without the log. So generally speaking, to describe this kind of isospin symmetry breaking in shell model calculations, the introduction of the INC forces or the isospin non-counseling forces into the effective interactions is required. And shell model calculation with the this isospin non-conserving forces usually includes Coulomb force that describes the loosely bound nature of the wave functions of the S-half orbit, can reproduce the observed mirror asymmetry in SD shell well. And additionally, the connection between the large mirror asymmetry in beta-decay transitions and the proton halo structure might provide a complementary means to identify halo nuclei. So let's then, with this in mind, let's move back to our silicon-25. The mirror asymmetry have been deduced for 5 transitions in mirror beta decays of silicon-25 and sodium-25. Although we can see the degree of Isospin-Symmetry Breaking is quite small for all 5 transitions. And but in order to contribute to the systematic understanding of the nature of mirror symmetry breaking, we still need to study if we can reproduce this symmetry in our shell model calculations. Then here the figure shows the experimental results and the shell model calculations done by our collaborators Aaron Medeligan and Alex Brown. The experimental Gamow-Teller transition strength are then denoted by the red bars respectively. The green and the purple bars represented the shell model calculations using the USDC and the USDI Hamiltonians, which directly incorporate Coulomb and other isospin breaking interactions. We can see both USDC and the USDI Hamiltonians reproduce the experimental data well. And yeah, it should be also noted that the theoretical uncertainty here reflects the uncertainty associated with the quenching factor. The development of these 2 new USD Hamiltonians has been detailed in our collaborators' paper here. You may refer to that for more detail. Then now let's talk about the most important state. We observed in aluminum-25, the lowest T equals 3½ IAS. It's short for isobaric analog state at 7.9 MeV. For this state, the proton partial width of this state was already determined to be 111 eV in the proton scattering measurement using polarized proton beams. And then, however, there are 2 magnesium-24 P-gamma reaction studies reported 2 gamma-ray partial width of this IAS. They are differed by a factor of 4. Okay, so we need to try to solve this conflict. We can extract the ratio of the gamma-ray intensity to the proton intensity, because we measure the beta-related proton branches and also the beta-related gamma-ray branches through this isobaric analog state, and we can combining with the literature proton width value yields a gamma-ray width of 2.1 eV. This is in agreement with the results reported by Morrison and more precise, but they are deviated from the Rogers results by a factor of 4. Moreover, our shell model calculations estimates this gamma ray width to be 2.9 and 2.4 eV respectively, using the USDC and the USDI Hamiltonians, both in agreement with our experimental results. So the discrepancy involving the gamma ray partial width of this IIS in the literature has been resolved in the shell model calculation, we also found another interesting phenomenon. We found that the proton decay width of this IIS is impossible to explain without considering the isospin mixing between the IIS and the nearby state, approximately 39 keV above, highlighted here in the red line here. So the isospin related problems have been active topics of both nuclear physics and particle physics research. So I'd like to elaborate on this point for a few minutes. In this decay of silicon-25 or any proton-rich nucleus, two kinds of states are expected to be populated in the beta decay. The T equals 3 IS and the T equals 1 states. That's for other excited states. So if we observe the proton emission from this IS, this will provide evidence that the isospin symmetry is broken, because the proton emission from the IS to the ground state of the proton daughter nucleus is just violating the isospin conservation rule. So so to study this isospin symmetry or isospin mixing phenomenon, usually to determine the amount of this isospin mixing in the isobaric analog state, experimentalists usually extract three quantities. The first one is the fragmentation of the BF, or the Fermi transition, or the Fermi transition strength, and also it extract the isospin mixing matrix element, nu, or the isospin impurity alpha squared. So in general, the Fermi transition strength is concentrated in just this one single state, the IES, which exhausts the sum rule of n minus z. But in a few cases, there aren't many experiments to study this, but there are a few cases that people observed the fragmentation of the Fermi transition strength. Okay, so we don't like to look into the details in this table. Let's look at some pie charts. So you can see here the fragmentation of the Fermi transition strength is represented by two sectors. The blue sectors represented the Fermi transition strength to the IES in each beta-decay daughter nucleus, and the red sector represents the fragmented Fermi strength splitted into a nearby state, just several tens of keVs above the IS or below that. So how about the silicon-25 observed in our experiment? We can show that one here. So we can see the sum of the rule of the Fermi transition strength fulfill the sum rule of Fermi strength equals 3, suggesting that the Fermi strength is merely concentrated on the IS. So it also means the fragmentation of the Fermi strength where isospin mixing is rather small in silicon-25 compared with the strong mixing observed for some special cases. I should also point out that we observed the 7902 keV IS. We observed the proton and the gamma-ray de-exciting this state, but we didn't observe any information for this 7939 keV state mixing with this IS. And here 0.01 is the strength just provided by the Shanghai model calculation. And this 3.0 is the Fermi strength we derived from our experimental data. The uncertainty I didn't put it here is 3.0 plus minus 0.5. So this means the fragmentation of the Fermi transition strength in silicon-25 in this case is quite small. And how about the other quantities? Let's see. Here is the isospin mixing matrix element. We observed this matrix element also for silicon-25. I put it here. It is small. We expect that because we didn't observe any decays from this state. So then the last one is the isospin impurity. All these 4 cases, they have some degrees of isospin impurity. How about silicon-25? Here, so you can see it's barely visible. So the main point I would say for this kind of experiments with both proton and gamma-ray spectroscopy method are required to identify these IIs and in order to test the predictions of the shell model homogeneous. So the understanding of this isospin forbidden processes will shed light on the mechanisms behind the isospin mixing, and will also be important to constrain the theoretical models. I should point out another issue is here. We can I also listed the aluminum 23 isospin mixing data here, but these data sets are still controversial because the previous measured results are not quite in good agreement with the sum rule, as you can see from this pie chart in the top left. The sum of the Fermi transition strength is 4.1, which is much higher than the sum rule. So there is some issues, there is some controversies here. So as I mentioned before, we also measured the aluminum 23 beta-delayed proton and beta-delayed gamma rays. We have the data set, so we will definitely investigate this case in the future. So stay tuned for more results related to this isospin symmetry breaking phenomenon. I think that's most of my results for the presentation. So to sum up, the silicon-25 beta-decays were measured by using the GADGET detection system here at NSCL, yielding lots of new and valuable spectroscopic information, as well as providing a stringent test for nuclear theories beyond the stability line. So this work also enhanced the utility of silicon-25 as a calibration standard for future experiments. Then last, I'd like to end my presentation by thanking all my collaborators, and thank you for coming to this seminar. As this is the last talk in the postdoctoral seminar series in 2020, I wish you a Merry Christmas and a blessed New Year. Now, I'd be happy to answer any questions you may have. Thank you.
Thank you. Any questions for the speaker? If so, please raise your hand in the participant window or just unmute yourself and ask. And I don't see any questions in the chat window. So you mentioned in the title the astrophysical implications of your results. Can you elaborate a little bit about that?
Yeah, the astrophysics implication. I should go back to the table I have here. So actually, in this case, for the silicon-25, sorry too much. The astrophysically interesting questions have already been solved. So it's because the proton decay daughter of the aluminum 25 is magnesium 24. So there are lots of magnesium 24 P gamma reaction measurements, direct measurements. So there isn't much room we can improve for the astrophysics questions for the silicon 25. So we initially decided to use this case to commissioning our setup. Then we study the property of the performance of our detection system well. Then we can go into the more challenging astrophysically open questions for like aluminum 23 and chlorine 31. They are both for nova nucleosynthesis and also magnesium 24 to investigate the X-ray burst light curve. So it's like for astrophysics, the other three cases are more interesting, I would say. Hope that answers your question.
Yes, thank you. Grisha, you have a hand up.
Yes, thank you, Anna. Well, Lijie, thank you for this very interesting results and exciting talk, actually. So I'm wondering, so you have observed very little isospin mixing for silicon 25, and I'm wondering that, are you going to test the isospin admixtures for other systems where there was previous data that isospin mixing is large? Don't you think it would be interesting to repeat the same sort of result using your very nice setup?
Yeah, that's a great question. So let me go to this table. So the reason I always find this isospin mixing question interesting is there aren't many observables that are sensitive to isospin mixing. So, and there aren't many experiments to study this. This is, to the best of my knowledge, maybe this is a little outdated. There are only 5 experiments. I didn't talk about this much. Is the nickel 53. This one, the isospin mixing is also extremely small. The matrix element is just 3 keV. So, so for the other 4 cases, we already measured the chlorine 31 decay to sulfur 31. This case, I believe this one is already well determined. And 2 other groups in Europe measured the copper 55. And sorry, this one is from the Florida State University, and the last one, the zinc 56, was measured by the ISOD facility. And so I believe these ones are the cases that are already well measured. I guess the only one remains unsolved is this aluminum 23 decay to magnesium 23, because the previously determined Fermi transition strengths, they just don't add up. So this one definitely needs more work to investigate. And we already have the data. The analysis is still underway. So we hope to achieve some good results from this case. So thanks for the question.
Right. Excellent. Thank you. Looking forward to see the results.
Thank you.
Any other questions or comments for the talk?
Oh, I can see my wife is also in the audience. That's a little surprise considering the time difference. Yeah, I should thank her for all these years support. She's a microbiologist. I hope this seminar isn't quite boring to her.
Yeah. Okay. If there are no more questions, thank you all for participating. This is our last seminar for this year, so have a happy holidays and all the best in New Year. And let me advertise the first seminar of the next year, which will be January 7th, and it will be Notre Dame's Nirupama Sen Sharma talking about wobbly gold nuclei. Thank you very much.
Thank you for coming.